Now, occasionally, it is the case that the area between of a region between two curves, or more than two curves, right, three curves perhaps, can be found just the way that we've described in previous videos, which is to say, we take a vertical area basically be between the limits of integration x1 to x2 when we take the top function minus the bottom function. But sometimes it's actually very useful to be able to do this as a function of y rather than a function of x. Now, as an exercise, you should go ahead and take a few moments and try this out for yourself. Imagine that we have this arrangement. We want to find the area of the region bounded by the curves f of x equals 4 over x here in purple, x equals 0, which is the vertical line of the y-axis, y equals 1 here in orange, and y equals 4 here in green. And if we did that using our vertical curves, of course, if we're doing it vertically, we might imagine this as being two different dx regions, one from 0 to 1 and then one from 1 to 4, where these curves all intersect, and putting that all together. It seems like a lot of work to me, so I'm going to try it a little bit differently. For convenience, it might actually be more helpful to be able to take this to be an area as we go from left to right. So if we imagine instead that instead of having a dx strip, we have a dy strip instead, we can maybe set this up in such a way that we only really have to go through one integral to do it, from y equals 1 to y equals 4, rather than two separate integrals going from 0 to 1 and another one from 1 to 4. Well, how do we get there from here? Of course, that means that we have to have a function in terms of y. The nice thing is we have an easy one in this case. We've got y equals 4 over x, which can be easily rewritten so that x is equal to 4 over y. And now we might note that, well, all right, to the right of the y-axis, we have the curve x equals 4 over y, and to the left, of course, we just have the line yx equals 0, right? So that's actually a bottom boundary for us. So really our setup is going to look like this. We're going to take a definite integral, only this time we're going to set it up on the interval from 1 to 4 of the function 4 over y dy. Very interesting. Well, we might recognize this one as a type of integral where we're going to take 4 times the antiderivative, or sorry, the definite integral from 0 to 4 of dy over y. So this is going to become 4 times the natural logarithm of y evaluated from 1 to 4. That's actually not a bad one to evaluate. We're going to get 4 times the quantity natural logarithm of 4 minus the natural logarithm at 1. Well, the natural logarithm of 1 turns out to be 0, and so our area will be 4 times the natural logarithm of 4, which we could approximate using a calculator if we really wanted to. That would be the natural logarithm of 4 times 4, and we see 5.545 or something like that. We'll just go ahead and keep that rounding right there. So 5.545 if we really needed to get some sort of accuracy numerically right here. But I like the exact value answers myself, and if you can give those, you're doing pretty well.